So good morning to all. So we should start right now today's session. I would request Professor Sibaji Raha, former director of Bose Institute, to chair this session. Sir.
Good morning to all of you, and it's nice to be greeted. So, without further ado, let's go on to invite the first speaker of the session, Barbara Riacha from LBL Berkeley.
And UC Berkeley.
And UC Berkeley, of course. I think the organizers would like to greet her first. Small token of our appreciation. Thank you. And Barbara will tell us about the experimental studies of transport in dense gluon matter. Barbara, you've got 45 minutes. Do you want me to give you a signal at 5 minutes before?
So as soon as my slides are up, I'll start. Slideshow. All right. So thank you very much for the invitation, and it's very exciting to be here in India in person. Yay. So today is my pleasure to talk to you about experimental studies of transport in dense QCD matter. Oops. And unfortunately, Bikash is not here, but I did want to acknowledge how much fun it's been over these past decades to study matter under extreme conditions with Bikash. He has inspired us to look at the quark gluon plasma both in whoa, okay, that's not what I want. Where's the laser pointer on this thing? Sorry, didn't do my homework. No, I don't do it. Okay. So, of course, Bikash has been looking at quark gluon plasma both in the macrocosm microsecond or so after the Big Bang, and also the way that we make it by looking at the quarks and gluons deep inside nuclei and heating them up with large colliders. So, transport properties. Now, if you open up your statistical mechanics textbook and you go to chapter 14 to the kinetic theory section, you find out that transport is pretty well defined. That transporting particles is, of course, diffusion, and that's something that we can, in fact, experimentally study in quark gluon plasma, in particular by looking at the heavy quarks. We could tag where they were made and figure out how they end up. If you then go on further in the chapter, you find out, well, that thermal conductivity is the transport of energy.
Microphone is muted. No sound.
Microphone is muted. Well, looks like it's on. I don't know. I'm supposed to talk to the laptop. So my choice, let's see if, is this any better, Shoji? Can you hear me now? It says it's muted on the... All right. Okay, I'm going back to the slides and screen. Sorry about that. Thank you for telling me. So I already talked about the diffusion as the transport of particles. So for the transport of energy, we can see how much energy is lost from fast quarks or gluons traversing the quark-gluon plasma. And by looking at the patterns of particle production, we can figure out where the lost energy goes. And there, of course, an interesting and important question is to ask, do we actually know how to calculate the energy loss in transport? We have a lot of calculations available using perturbative QCD, and it's important, I think, experimentally to check what do they get right and what do they get wrong. And then, of course, going further, if you'd like to learn about viscosity, well, that's the transport of transverse momentum. And as you already heard yesterday from Federico, you measure the particle collective flows, you can extract viscosity, and I'll talk a little more about how we do that. Now, I'm going to give this talk in a slightly different order. I'm going to start with the viscosity, since that's something we already have started to discuss, then the diffusion and the thermal conductivity. And one of the things I want to focus on is how we use jets and jet substructure to study the transport of energy and eventually particles. Now, though most of my talk is going to be about transport in hot, dense QCD matter, because that's where we have a lot of data, I will answer the obvious next question, which is what about transport in cold QCD matter? I'll tell you how we can have a look at that at the electron-ion collider, and then I'll say a couple words about hadronization. So, a clear question that one should start out with, one's going to talk about transport, is how does QCD matter work? What's plotted here is how the energy density depends on the temperature. This is from a calculation on lattice QCD. And you see a very large rise in the energy density at a critical temperature, as you expect from a phase transition from hadronic matter to quark-gluon plasma. And then you see a flattening of the energy density with temperature thereon. And if you look, you can see that the lattice calculation gets pretty close to the ideal gas limit. And so as a result, many people expected before Rick started up that the quark-gluon plasma would have transport properties pretty similar to an ideal gas. Now, if you think about this a little bit deeper, you say, well, okay, the range of the strong interaction is about a Fermi. In a hot, dense quark-gluon plasma, the number of gluons inside a radius of about a Fermi is actually a large number. And so you immediately think, well, it actually should not behave like an ideal gas. Shouldn't there be a lot of many-body interactions? And those would cause very interesting transport properties. So those of you who are not heavy ion physics practitioners are probably wondering, how do you actually measure anything about transport in quark-gluon plasma? The trivial answer, of course, is you measure the particles coming out. But if you look in more detail, this is a sort of a cartoon of the transverse momentum distribution of the hadrons coming out. If you look at low transverse momentum, you're looking at particles that are radiated from the bulk medium. In the language of plasma physics, these would be internal probes of the quark-gluon plasma. Conversely, if you look at the higher momentum end, then you actually are looking at probes with a different scale than the temperature of the plasma. They're like an external probe of the quark-gluon plasma, although they're auto-generated in the collisions themselves. And in effect, what you're doing by measuring these high momentum particles is looking at the remnants of partons, quarks and gluons that came in, had a high transverse momentum exchange, so a hard scattering, and then came out through the plasma. If you look and see how well do they penetrate the plasma, then you learn about the plasma transport properties. Now, for any of the few students who might have dared to venture back after yesterday, you know that a really good experiment has to have a control. And so in measuring transport in quark-gluon plasma, we also have a control. And those are particles that don't feel the strong interaction, but rather interact by the electromagnetic interactions, such as photons, or weak interactions, W's and Z's. Oops. So let me start with the viscosity. As you saw yesterday from Federico, we actually can measure the collective flows by looking at these particles that have a low momentum, so this part of the spectrum. Let's start with this here cartoon of the interaction just after two heavy ions have passed one another. And here you have a sort of an almond shape, which is where they overlapped. Now, if you look at this from the beam's eye view, you see that indeed you have an asymmetry in coordinate space. Now, of course, if you have a lot of collisions among the particles in here, that asymmetry in coordinate space is translated to an anisotropy in momentum space, just as you would expect. And that's something that we can measure. The way we measure it, the easiest way to measure it, is by looking at the opening angle difference between all the particles coming out of the quark gluon plasma. If there's no anisotropy, then that opening angle difference distribution should be flat. And here you can see some early data from Rick, and lo and behold, it's not flat. It's got a characteristic shape, and we then subject that to Fourier analysis. And the second Fourier component is the amplitude of this deviation from flat, and that is our elliptic flow. As you saw yesterday, if you plot the second Fourier coefficient per quark divided by the transverse kinetic energy, and then versus the transverse kinetic energy per quark, you see that all the different particles actually fall onto a common curve. It's very common at Rick. It's slightly less tightly clustered at the LHC. Nevertheless, one can then translate this V2 pattern by comparing with hydrodynamics calculations, as you heard about yesterday. And from the hydrodynamics, you can then extract what the viscosity to entropy ratio is. And you find that quark gluon plasma has a lower viscosity per particle, essentially, than any of the other systems studied so far. And interestingly and surprisingly, that's even true in the very small systems one makes in P-lead and even high multiplicity proton-proton collisions. So we see this kind of flow, and we see a very similar viscosity to entropy ratio, even in very small droplets of quark gluon plasma. Now, looking under the hood of the hydrodynamics calculations, then you can actually extract the eta over S value, which is somewhere pretty near 1 over 2 pi. And as you heard, that's kind of a limit from the uncertainty principle. And that tells you that you're nowhere near the ideal gas behavior that one might have naively expected. The interaction cross-section is much, much larger, as you would expect due to the many body interactions. So, okay, what's next? Where are we going with the collective flow, viscosity, measurements, and understanding? If you read this little summary from the recent Quark Matter 22 meeting, well, you see that the measurements have become very precise. And right now, the uncertainties don't come from statistical uncertainties in the measurement anymore, but rather the fact that nature does a time integral for us. We can only look at the particles at the end of the collision. And of course, that the dynamics are affected not just by the quark gluon plasma, but by the hadronic phase and the process of atomization itself. So what one really needs is to look at things like higher order correlations, compare the flow as a function of the particle, the quark mass, and by varying the system geometry, using different nuclei in the beams, and the system size, including very small systems, one can then better disentangle the initial state geometry, which sets that initial asymmetry and the actual viscosity of the quark gluon plasma in order to make these great big uncertainties smaller. I think that's our next aim in that direction. Now, I mentioned that we would like to look at the heavy quark flows also. In fact, we have done that. What's shown here is the V2, this second Fourier coefficient that measures the collective flow, the anisotropy in the momentum space. And you can see that these V2 values for heavy quarks via d mesons are also significant. They're in fact about the same as what we see from light hadrons. All these different colored lines are many different models of the collision that include both the collision dynamics, the hydrodynamical expansion, and then the interaction of the charm quark with the quark gluon plasma. As you can see, they don't all give the exact same answer. There are a lot of differences in the models, both in the interaction of the heavy quarks with the plasma and also with the collision dynamics. This over here is the ratio, which I'm going to talk about a lot starting momentarily, but it's called RAA, and that's simply the ratio of how many d mesons do you see in a lead-lead collision compared to how many you expect from the comparable number of independent proton-proton collisions. And you can see, here's 1, so that ratio is something crazy different from 1. And of course, if you have a lot of collisions, a lot of energy loss, you have honest-to-goodness diffusion, then you don't expect that ratio to be 1. And so the models calculate this quantity as well. And then one can, by comparing the models to the data, extract what the diffusion coefficient looks like. So if you just look at all of these models and what diffusion coefficient they then predict, the first thing you see is that it's kind of a mess. But then you actually look that you can see that near the critical temperature for the phase transition to quark gluon plasma, they're actually, many of them are not so far apart. So one can then make a selection of which ones actually reproduce the heavy flavored data, and then pick out which of these models do the best. And that means that they've got a sensible combination of the evolution of the system plus the radiation of gluons from the charm quark as it traverses the quark gluon plasma and the effect of collisions of those heavy quarks with the plasma. And you can find out that the diffusion coefficient is somewhere between 1.5 and 4.5 divided by 2 pi times the temperature. And so that's right down here. Now, you can ask, is that what we should expect? Well, maybe we should. If you just try to calculate it perturbatively, you find out that you expect a diffusion coefficient that's much larger. However, if you look at the predictions from lattice QCD, which are these black points, actually that is what we should expect. Of course, in the lattice QCD calculations, the many-body interactions are taken into account. So let me now turn to energy transport. That is looking at the higher PT end of the spectrum. And for those of you who are members of ATLAS, you're probably laughing at me saying high PT is up to 10 GeV. It's just a cartoon, as you'll see in a moment. So what's the first thing you can do with these high PT particles? Well, start by counting them. So what you see here is, again, this RAA. It's the ratio of how many particles you see in lead-lead collisions compared to how many you would expect from the comparable number of proton-proton collisions. Here you see, if you count up all charged particles up to 100 GeV, and this is jets up to 300 GeV. So I wasn't actually lying when I said we're looking at high PT particles. And what you see is that they're far, far away from 1. Now you might ask if we know how to count. That's a perfectly fair question. And let me just point out that here, this RAA ratio for photons W's and Z's sits right at 1, as it should, since you don't expect any energy loss from photons. So we do know how to count. And then you have to take seriously the suppression of the heavy stuff, the high PT stuff, by a factor of somewhere between 2 and 4. So what we're actually seeing is if you have a hard scattering and then you look for this hard scattered particle coming out, you do have a lot of interactions with the quark gluon plasma, and so they lose a lot of energy and shifts them lower in PT. Then the obvious question is, well, what's going on? What is the mechanism of the energy loss? Is it radiation? Is it multiple scattering? And what combination thereof? So the way we quantify the parton energy loss is a variable we call Q hat. It's essentially the ratio of the mean, the typical PT transfer per scattering divided by the mean free path. Kind of not too surprising. Here you see the RAA, not just from the charged particles, they're shown in red and yellow here in this plot, but also from T mesons and B mesons. You see they all are giving you about the same answer. So once again, we play the same game. We constrain the theory by the measured RAA, and we can see how the theory tells us the partons are interacting in the expanding quark gluon plasma, and extract Q hat from the theory. And you find out that if you start out with a 10 GeV parton, so right over here where the energy loss is maximum, the Q hat value is somewhere between 1.2 and 2, depending on what temperature your quark gluon plasma is. You expect that that should be fairly large because you have many body interactions and a lot of interactions of your probe quark or gluon with medium. But for comparison, there have also been some calculations of what's expected for the energy loss of cold nuclear matter, and you'll notice that's about 100 times smaller. So to be a little bit more quantitative, here you can see, once again, this cacophony of colored curves compared, in this case, to the RAA for D mesons. And you can see if you just fit the light hadrons with a Bayesian fit process, you can extract the Q hat value. That's somewhere down here, given by this black dash line. If you add the extraction looking at the energy loss of the heavy quarks, you find out that those models which fit the data